right, everyone. Welcome to today's edition of the HEAD meeting. We'll have two amazing talks, and the first one will be remotely by Ralf Ballhausen. It's my pleasure to introduce Ralf. He's currently a postdoc at the University of Maryland and NASA's Goddard Space Flight Center. He got his PhD in 2021 from the University of Erlangen-Nuremberg. That's also where I did my PhD, and I shared a lot of very fun experiences with Ralf, including some skiing trips, and I'm happy that he can make it today to talk about XRISM. So Ralf moved to the University of Maryland and NASA Goddard Space Flight Center to join the XRISM science team and work on plasma modeling in support of the XRISM mission. His research interest focuses on X-ray binaries and accretion-powered neutron stars, photoionization modeling, atomic data, and laboratory astrophysics. Thanks for coming here, Ralf, virtually, and please take it away.
All right, thank you very much for the introduction and giving me the opportunity to present here today. So my name is Ralf Ballhausen, and I'll be talking about early XRISM results, in particular of high-mass X-ray binaries. And I just realized I misspelled XRISM already on the title slide, so that's a good start. But in any case, I'm sure most of you are familiar with X-ray binaries and how they work, so I'll be quite quick on this. But just to set the stage, we're talking about systems that consist of a massive star, a donor star, like or a B type star with a strong stellar wind, and a compact object like a neutron star or a black hole that accretes from the wind of that donor star. And then the release of the potential energy of this accretion process powers X-ray emission, and the X-rays get reabsorbed in the stellar wind, and they ionize the wind, which in turn affects how effectively the wind can be accelerated, the wind dynamics, but also the wind imprints its signature on the reprocessed X-ray radiation, and this is a great way to study the mechanisms of the systems. So we're interested in high-mass X-ray binaries for a number of reasons. For example, it's basically through the birth and the evolution and ultimately death of stars that elements are synthesized and get finally deposited in the interstellar medium. This is also a mechanism to form dust grains in the ISM, but it's also important to understand the evolutionary tracks of these systems, supernova progenitors, and the population of compact objects that we see today. And also these systems lead to the evolution of compact binaries that are, for example, relevant for gravitational wave astrophysics. So one important thing to note here is that while we can broadly categorize these systems, for example, depending on the mass of their donor star or the type of their compact object, like whether it's a neutron star binary system or a black hole binary system, all the individual sources are really quite different when it comes to the details of how they behave. And a lot of this depends on, for example, exactly what the stellar type is, what the masses are, or the mass ratio of these systems is, what the orbital separation or its eccentricity is in an individual source, but then also, for example, what the luminosity of the actual luminosity of the compact object is, and this is connected, for example, in a neutron star binary, also to things like how fast the neutron star spins or what its magnetic field is. So the whole field of studying X-ray binaries is not new. In fact, X-ray binaries have been virtually studied from the very beginning of X-ray astronomy. But what has changed fairly recently with the launch of XRISM is that we can perform high-resolution X-ray spectroscopy also for high Z elements, most notably iron. So the X-ray mission, the X-ray imaging and spectroscopy mission, was successfully launched in September 2023. So we're a little over the second launch anniversary now as the recovery mission, the ill-fated Hitomi satellite, and it carries two instruments. One is the resolve instrument, the microcalorimeter spectrometer, and the second one is a CCD based imaging spectrometer that is very similar to the XRISM instrument that flew on Suzaku. So the resolve microcalorimeter is the instrument that's getting a lot of attention right now because this is truly revolutionary. This is a microcalorimeter spectrometer that has an energy resolution of about 5 eV. The angular resolution is the PSF, so lower. It's not as fantastic as some other instruments, but it still allows to do spatial resolved spectroscopy for extended sources. The energy range that we currently have is a little bit limited because there is still an issue with an aperture door that is blocking the soft X-ray, but for bright point sources, we can cover this range with gratings like the XMM RGS or the Chandra gratings. And yeah, so these are basically the key parameters of this instrument. In particular, it allows us to study high energy transitions of say iron at an energy resolution of a few eV. So here's a picture on the right-hand side of how this microcalorimeter array looks like. This is a grid of 6 by 6 individual pixels, and the way this works, or basically how all microcalorimeter X-ray spectrometer work, is that photons get absorbed, the individual photons get absorbed by these pixels, and you measure the temperature increase of that pixel due to the energy deposition, and then the resolution is basically determined by how accurately you can reconstruct the deposited energy from the rise and the decay of that temperature of that individual pixel. So it depends, for example, on the total count rate that these pixels get, because it takes a little while for the individual pixels to cool down again after an incident photon. So now turning to the astrophysical sources, one of the very famous and very special high-mass X-ray binaries that XRISM observed very early on in its mission was Cygnus X3. And Cygnus X3 is quite extraordinary in that it has a Wolf-Rayet companion star. So it's a massive evolved star that's characterized by depletion of hydrogen and very strong optically thick stellar winds and high mass loss rates that are of the order of 10 to the negative 5 solar masses per year. So the X-ray source is quite obscured by the stellar wind, and it orbits the Wolf-Rayet star in a close tight orbit with an orbital period of a little less than 5 hours. So this is the iron K band spectrum taken with XRISM Resolve. And you can already see that this is very rich in features. So in particular, what you can see is like a fairly weak, broad iron K alpha emission feature on 6.4 keV, and then a very prominent emission triplet by mostly helium-like iron 25. But in particular, the resonance line at 6.7 keV forms a P-Cygni-like profile. so there is both emission and absorption in this system. And then there's a much broader hydrogen like iron 26 line. And we've been able to model this with multi-component photoionization models that basically model the different emission components and the different absorption components, which require different velocity shifts and broadening to get all these line ratios reproduced well. But like I said, this is a very the system is in a very close orbit, and here you can see on the right, you can see the XRISM light curve of the system, and the whole XRISM observation spanned about 7 orbital cycles of the system. So each of these peaks basically just shows you the orbital modulation of the system. So with this, we're in the lucky position that we can do orbital resolved spectroscopy. So we can slice the whole observation up and look at different orbital phases. This is shown here, where you can see basically the spectrum that I showed you a few slides ago, orbital average for individual orbital phases. You can actually see that these spectra also vary significantly as a function of just the orbital phase of the compact object. So finally, with this, we're able to reconstruct orbital radial velocity curves that are shown here. And what's interesting to note is that we get very different radial velocity curves for the emission lines that we see compared to the absorption lines that we see. So the absorption is overall blue shifted, and the amplitude of the variability is much smaller as compared to the emission lines that are redshifted by just about 50 kilometers per second, but have a much larger amplitude. So the next source I wanted to show is Centaurus X3. That's a neutron star binary system with an O star. So that is the star that has a significantly lower mass loss rate, and the wind of the system is much more optically thin than what we saw in Cygnus X3. It's an eclipsing system with a very circular orbit. The orbital period is larger, and this was also a XRISM PV target that I was involved in. So here's the XRISM resolved spectrum on the left, and you can already see at first glance that this looks fundamentally different from the SIG X3 spectrum, in that you see a narrow iron alpha feature, and you basically only see these emission lines of iron, not the strong absorption and P signal line profiles that I showed you for SIG X3. And again, the XRISM observation here was about 160 kiloseconds, and this basically covered an entire orbital revolution of the system. So again, we're able to measure the line radial velocity shifts here of the neutral line, and this is shown here on the right, and compare to the different velocity curves that you would get from the motion of the compact object and the O star. So what we see here is that the line also shows the sinusoidal variation of it as a function of orbit, but the velocity amplitude is significantly higher from what you would get from the O star. But it's also not quite as high as what you get from the neutron star. So the neutron star is just from calculating the mass, its orbital velocity from its mass ratio and the orbital period is still significantly higher than what we see from the K line. So this brings up the question again where these iron lines are formed. So one of the suggested line forming locations was reflection from the O-star surface, but this clearly doesn't produce the observed orbital velocity curves, and a similar problem is clear from for the neutron star. So there must be some material that is closer to the neutron star, still dense enough that it doesn't get too highly ionized, but still produces this orbital velocity curve, and also like explosive line broadening of a few hundred kilometers per second. Centaurus X3 also shows these shows ionized iron lines. So here's a close-up of the helium-like emission complex with the resonance forbidden and intercombination lines, and so basically the ratio of these lines are usually used as diagnostics for plasma diagnostics, because the intensity ratios of these lines are sensitive to temperature and flux, temperature and density.
About 5 minutes.
Thanks. Okay. So observing these lines has been typically done with grading instruments for low C elements. So this is basically a plasma diagnostic that has been applied to a lot of systems with gratings, and was actually originally, I think, proposed for the Sun. But XRISM really allows us to do this for iron, and in particular in this paper we discuss the effect of density, but also UV field, and how this affects quantitatively this line ratio, because basically the way this ratio is a probe of density is that you have collisional depopulation of this forbidden upper level, the upper level of the forbidden transition of the C line, which in principle is something that you can also do via UV photons. So here you can really measure these line ratios and try to understand where actually this plasma is, and what the local conditions are that give rise to these observed profiles. So as I'm running out of time, I'll just jump ahead to the next. Like last target that I want to discuss, this is 3301-2, and that's a hypergiant donor star, also with a neutron star that has a much larger orbital period, and the orbit is highly eccentric. So the stellar wind in this system is optically thick again. It's slower and dense, and again leads to a heavy obscuration, similar to Cygnus X3, where we also observe line of sight column densities of the order of 10 to the 24 particles per centimeter square. So this system was observed as part of the GEO program, close to a flare that happens basically close to every periostron passage. So here's the long-term light curve, and you see this big flare here that basically happens every periostron passage. So XRISM observed this toward the end of the flare, but then you see also the light curve itself on shorter timescales is very variable. And this is the X-ray spectrum of G301-2, again, just a close-up of the iron K-band. And what you can see again is this very strong iron emission line that's again very narrow. You can actually already see the split in the fine structure components of the K line. And in addition, this line also has a very pronounced Compton shoulder feature. That's this, I don't know whether you can see my cursor, that's this bumpy feature on the left, in the red wing of the line. It's basically formed by Compton scattering of line photons, of fluorescent line photons, in a cool ambient medium where they on average lose energy and form this shoulder-like feature. So measuring this shoulder, constraining the shape of the shoulder, allows us to probe the temperature of that medium, because if the temperature gets high, then this feature gets broader, and at a certain temperature just gets smeared out. So what we're able to do is set limits on the temperature of this plasma to a few eV. And right now we're comparing this with our photoionization calculations to see how these temperatures line up in a photoionized wind. So I think I'm running out of time, so I'll leave my summary slide up, and I'm happy to take questions.
We have questions. I'll start with one. So for Cygnus X3, kind of thinking out loud while I'm formulating the question, we can't really detect the broad relativistically smeared reflection so well with XRISM, but can you say anything about the structure in the about the inner accretion flow in Cygnus X3, like whether it may be like a funnel shape and a ULX type source, as was speculated based on the XP results, or is it not really probable with XRISM?
So let's about reflection modeling. I'm not really a reflection expert on reflection modeling. I think so we see a broad iron line. If I go back to this, I think you can see basically this is the iron line that we see, but it's not, from what I remember, like from the reflection spectra that I see, you see a more asymmetric line that has an extended red wing. And actually, I think a lot of these observations have been done with also, say, XMM, because for those it's very important to get actually extremely good signal to noise. So
it probes more the stellar wind, really.
So right here we're probing more conditions of the stellar wind, but I'll also say we haven't tried modeling the near neutral line or lowly ionized line with a reflection line model. that's, yeah, we haven't tried that, so I'm afraid I can't really say.
Yeah, Peter.
Hi, this is Peter. Thank you for the nice talk. I have a question about the comparison of the three sources. So SIGX3 and SENX3, they show strong ionized lines in absorption or emission, but GX301, it only shows neutral. Can you speculate why?
There are also some ionized lines, but they're much, much weaker. So, right, so the material overall has to be neutral or more neutral. And yeah, actually, it's a great question. Why? So basically, the way to get to this would either be higher densities or larger distances from the compact object. That basically lead to geometric dilution of the radiation field, and overall this brings the ionization down. But yeah, so it has to be some sort of a combination of these two things. The orbits are very different. SIGX3 really is basically always inside the stellar wind shell of this Fourier star, and GX301-2 basically only dips into this close to the periastron. But yeah, I don't have a one definitive answer to other than it's basically the wind in SIGX3 is much more ionized, and that's basically typically a combination of your density and your radiation field.